In this work, we introduce FunFact, a framework for building probabilistic functional 3D scene graphs through factor graph reasoning. Functional scene understanding aims to infer how objects interact in a scene. For example, in a room, we may want to know which object to interact with to change the illumination. However, this problem is challenging for two main reasons. First, many functional relations are visually ambiguous. For example, in the stove shown here, the left knob may control either the top burner or the bottom burner. If the relation cannot be verified visually, the system should at least represent this uncertainty rather than make an overconfident prediction. Second, functional relations are interdependent. The confidence of one relation can change when we observe more of the scene. For example, when entering a new room, if we see a wall switch and a nearby ceiling light, we may be highly confident that the switch controls that light. But after turning around and seeing another ceiling light, our confidence should be redistributed between the two possible connections. This means functional prediction should not be performed only on isolated object pairs, it should consider the full scene context. To address these challenges, our core idea is to convert the functional scene graph into a dual factor graph. In the original functional scene graph, edges represent possible functional relations. In our dual factor graph, these edges become binary variables indicating whether each relation exists. Ambiguity is encoded through factor potentials, and scene-wide context is incorporated through joint inference. To put this idea into practice, our full pipeline builds a probabilistic, open vocabulary functional 3D scene graph from posed RGBD images. Starting from an RGBD sequence, we first reconstruct the 3D scene and identify objects and their functional parts. We then use a language model to propose semantically plausible functional templates, such as a switch toggles a light. Based on these templates, we connect all matching object pairs with candidate functional edges. This initial graph is intentionally overconnected, and the factor graph refines it by estimating the probability of each edge and pruning unlikely connections. For 3D scene reconstruction, we use a vision language model to identify functional objects. We then ground these entities in the images using grounding deno. For objects with functional parts, we further ground the parts within object-centric crops. Finally, all object and part pixels, together with their 2D deno features, are lifted and fused across views to create an object and part-centric 3D map. Next, we construct the factor graph. Each candidate functional edge becomes a binary variable, and we define factor potentials using two priors. The first is a proximity prior, which favors closer functional connections. For example, a nearby switch is more likely to control a nearby light than a distant one. The second is a cardinality prior, which captures constraints such as one-on-one relationships. For example, switch-light relations are often mutually exclusive. One switch may control one light, or one light may be controlled by one switch. This prior helps avoid overconfidence in a single connection when multiple plausible alternatives exist. Once the factor graph is built, we run loopy belief propagation to perform joint inference. The output is a marginal probability for each functional edge. These probabilities represent edge confidences that account for both local ambiguity and global scene context. We evaluate FunFact in two settings. First, on FunGraph 3D, we follow the standard evaluation protocol and report recall at top K for both object reconstruction and functional edge prediction. FunFact consistently outperforms the open FunGraph baseline. Second, we introduce FunThor, a new dataset built from AI2 Thor scenes. Because the annotations are automatically derived from simulator ground truth, FunThor provides dense functional edge annotations, allowing us to additionally evaluate precision and F1 score. FunFact achieves higher precision, recall, and F1 than the baseline. It also achieves lower expected calibration error, meaning its predicted probabilities are better calibrated. Finally, we show a qualitative example here. FunFact correctly predicts functional relations such as handle opens cabinet and power outlet provides electricity to kettle, which are included in the ground truth annotations. It also predicts plausible open vocabulary relations that are missing from the ground truth, such as oven mitt handles hot pot. You can find more qualitative results and interactive demos on our project page. Thank you for watching.